Summary. Let's summarize the topics which we have learned in the chapter. If a quantity y varies with another quantity x satisfying some rule y equals to fx, then dy dx or f dash x represents the rate of change of y with respect to x, and f dash x naught represents the rate of change of y with respect to x at x equals to x naught. If two variables x and y are varying with respect to another variable t, that is, if x is equal to ft and y equals to gt, then by chain rule dy dx equals dy dt divided by dx dt, provided dx dt is not equal to 0. A function is said to be a increasing on an interval a comma b if x1 is less than x2 in a comma b and f of x1 is less than equal to f of x2 for all x1 x2 belonging to a comma b. Alternatively, if f dash x is greater than equal to 0 for each x in a comma b. B decreasing on a comma b if x1 less than x2 in a comma b, f of x1 greater than equal to f of x2 for all x1 comma x2 belonging to a comma b. Alternatively, if f dash x is less than equal to 0 for each x in open interval a comma b. The equation of the tangent at x0 comma y0 to the curve y equals to fx is given by y minus y0 is equal to dy dx into x minus x0. If dy dx does not exist at the point x0 comma y0, then the tangent at this point is parallel to y-axis and its equation is x equal to x0. If the tangent to a curve y equals to fx at x equals to x0 is parallel to x-axis, then dy dx equals to 0. Equation of the normal to the curve y equals to fx at a point x0 comma y0 is given by y minus y0 equals minus 1 by dy dx into x minus x0. If dy dx at the point x0 comma y0 is 0, then the equation of the normal is x equals to x0. A point C in the domain of a function f at which either f dash c equals to 0 or f is not differentiable is called a critical point of f. First derivative test. Let f be a function defined on an open interval I and f be continuous at a critical point c in I. Then number 1. If f dash x changes sign from positive to negative as x increases through c, that is, if f dash x is greater than 0 at every point sufficiently close to and to the left of c, and f dash x is less than 0 at every point sufficiently close to and to the right of c, then c is a point of local maxima. Number 2. If f dash x changes sign from negative to positive as x increases through c, that is, if f dash x is less than 0 at every point sufficiently close to and to the left of c, and f dash x is greater than 0 at every point sufficiently close to and to the right of c, then c is a point of local minima. Number 3. If f dash x does not change sign as x increases through c, then c is neither a point of local maxima nor a point of local minima. In fact, such a point is called point of inflection. Second derivative test. Let f be a function defined on an interval I and c belongs to I. Let f be twice differentiable at c. Then, number 1. X equals to c is the point of local maxima if f dash c is equal to 0 and f double dash c is less than 0. The value fc is local maximum value of f. Number 2. x equal to c is a point of local minima if f dash c equals to 0 and f double dash c is greater than 0. In this case, fc is local minimum value of f. Number 3. The test fails if f dash c equals to 0 and f double dash c equals to 0. In this case, we go back to the first derivative test and find whether c is a point of maxima, minima, or a point of inflection. Working rule for finding absolute maxima and or absolute minima. Step 1. Find all critical points of f in the interval, that is, find points x where either f dash x equals to 0 or f is not differentiable. Step 2. Take the endpoints of the interval. Step 3. At all these points listed in step 1 and step 2, calculate the values of f. Step 4. Identify the maximum and minimum values of f out of the values calculated in step 3. This maximum value will be the absolute maximum value of f and the minimum value will be the absolute minimum value of f. That's all. Surely you would have loved the chapter and mastered all the concepts.